Hello everyone. Today I will present the paper Adversarial Discriminative Domain Adaptation, also known as ADDA, which was published at CVPR 2017 by Eric Zheng, Judy Hoffman, Kate Sanko, and Trevor Darrell. ADDA is a widely recognized paper in the domain adaptation field, with approximately 6,000 citations to date. It introduces an adversarial learning approach for unsupervised domain adaptation, aiming to address the challenge of domain shift in machine learning models. What makes ADDA stand out is its flexible training framework, which uses a separate target encoder combined with adversarial feature learning, making it more effective than previous methods. Motivation. Deep learning models often fail when applied to a different, but related dataset due to domain shift. This results in poor generalization when the source and target distributions differ, as illustrated in the figure. Key contribution. The paper proposes ADDA Adversarial Discriminative Domain Adaptation, a GAN-based domain adaptation DA method. It aligns feature distributions between a labeled source domain and an unlabeled target domain using adversarial training. Unlike previous methods, ADDA trains a separate target encoder, improving flexibility and adaptation. Impact performance. ADDA achieves state-of-the-art SOTA results on various domain adaptation tasks. ADD demonstrates strong generalization across multiple datasets, proving the effectiveness of adversarial learning in domain adaptation. Before diving into the details, let me first give you an overview of today's presentation. 1. Domain adaptation. I will start with a brief introduction to domain adaptation, explaining why it is important and how it addresses the domain shift problem in machine learning. 2. Adversarial Discriminative Domain Adaptation ADDA. Next, I will introduce ADDA, the main focus of this presentation. I will explain how it works, its training process, and why it outperforms traditional domain adaptation methods. 3. Generative Adversarial Networks GANs. Since ADDA is based on adversarial learning, I will briefly discuss GANs and how their concepts are applied in ADDA to align feature distributions. 4. Experiments. I will then go over the experiments conducted in the paper, including the datasets used for evaluation. 5. Results. I will present the quantitative results, comparing ADDA to previous domain adaptation methods. 6. Conclusion discussion. Finally, I will summarize the key takeaways of ADDA, discuss its strengths and limitations, and explore potential future directions for improving adversarial domain adaptation. With that, let's begin with the first section, domain adaptation.
I will have two parts. The first part is some background of visual domain adaptation, and the second part will be the overview of existing visual domain adaptation settings. I want to share some ideas from the very standard visual recognition task. As you can see from this page, assume we are trying to train a model, an image classifier, to do classification. And we have a source data set. In the source data set, we have images from multiple categories. This is very standard. And in most cases, those images are from the one single domain. This is a very standard setting. And a common assumption or a hypothesis is that we assume the source data and target data, they are from the same or very similar distribution. As you can tell from this figure, right? We have the distribution of source domain PS of X. X here refers to the images. And you can see the other distribution is PT of X. T refers to target data or test data. And those two distributions are very similar. And a benefit of this assumption is that if the data sets conform to this assumption, your model trained from the training data set will be easily adapted to the target data set. And you will end up with getting very high accuracy for classification. This is a very ideal assumption. However, in reality, we usually have the actual situation when the source data and target data, they are actually from different distributions, as you can see from this figure, right? So the source distribution is similar as before, but for target data domain, in this case, you can see some visual differences by comparing the source images and target images. Although they represent the same concept, the backpack and the bicycle, but this one is the images from real world, right? They have some background, they have some noise on the images, but the target domain, in this example, we have images for the same visual category, but these images, they have quite different characteristics, right? They have different properties. For example, they have very clean background, white background, and this is an icon, not a real bicycle. Although they are similar and they are representing the same visual concept. So this kind of differences across the source domain, target domain, if you want to mathematically understand the difference, then they can be viewed as the difference between the two distributions, right? This is the orange one, represent the data distribution in source domain, and this is the blue distribution, which represents the target domain. Then in this case, it's very hard to train image classifiers which can do very well by only using the source data, right? Because it's a huge difference between the source and target data. So here is the motivation of visual domain adaptation. The goal is that we want to adapt the model from source domain, target domain, and improve the accuracy in target domain. Before thinking about how to achieve domain adaptation, let's say if you train a classifier in a source domain, let's say we have a bunch of images for this class, for the class backpack, and the second class is for bicycle. We have a number of samples for each class. And for this binary classification task, you may have this classifier. This is a model learned from dataset. You want to separate two classes. If you simply and directly apply this model to your target dataset, you can imagine, right? So it's very hard to separate the two classes in target domain because they have different distributions. And therefore, if you look at the accuracy in target domain, it will be very low. And this kind of issue is mainly due to domain gap. Due to domain gap, you will see a difference between the source domain, target domain, and the difference between the two distributions. Therefore, the performance of the model in target domain will be very low. You may wonder why this kind of domain gap will occur in reality. There are many, many different reasons. So in general, you can think about the out of distribution scenarios, right? So due to various types of the distribution shift, such as covariance shift, meaning that the feature distribution from source domain, target domain are quite different. And concept shift. For example, you have 10 classes for training in your source data set, but in a target data set, you may have 11 or 12 or even more classes. So this kind of shift, we call it concept shift. And even more, you have some scenarios with temporal shift. Over time, the data distribution will be changed, right? So in general, all those things could be the cause of the domain gap. In particular, you can also see some concrete examples. Let's say the data collection manners might be different. For example, the images of same object, if you use different camera, then they will give you some different visual experiences, visual appearances, right? And also, if you think about the same person as a person real ID as one example, due to different illustration and sorry, this should be illumination and pose and color and background, right? Then those kind of differences will also cause domain gap between the source and target domains. And even more, if you think about the image styles, real images versus simulation images, and even different cultural background and of the images, we have a lot of possible reasons for the domain gap. In other words, domain gap is a realistic and very challenging problem. So it doesn't make sense if we simply use the model trained from one simple source domain and we assume this model can work well. I believe every one of you know that it's very hard to have this kind of strong assumption in reality. Then the research question is, how could we address this domain gap and how to improve the model training? Then that's the major motivation for visual domain adaptation. The key is that could we be able to develop a better algorithm by training the model in one or more source domains and part of the target domain in order to reduce domain gap and most importantly, to improve the model's performance in target domain. If you look at this figure again, our objective is to somehow reduce this gap to make them well aligned, and therefore the knowledge from the source domain, in other words, the classifier learned from source domain, can be well adapted to this target domain. That's the general idea behind domain adaptation. And domain adaptation is not a new problem. You may ask, okay, this is an old problem, maybe started for over 10 years. Why do you want to present this tutorial at CVPR in 2023, right? The reason is that although the standard setting of domain adaptation is an old problem, we also notice there are many different new settings in domain adaptation, which can be used in many realistic problems nowadays. So it's an older problem, but there are also many new flavors, many new perspectives we can think about and we can further develop. And meanwhile, more importantly, there are still many unsolved problems which will be covered in the last section of our tutorial. And that's why I want to give you a comprehensive picture of this domain to showcase, okay, how this domain evolves over years and what are the remaining problems. Here I want to discuss the categorization of domain adaptation methods. First, there are many different ways to categorize methods, as in many different topics, right? So here we want to highlight two different ways to categorize those methods. The first way is to separate the methods based on the label space relationship between the source and target domains. And the second one is to consider the privacy issue you used when you do the adaptation between source and target domain. I will show you more details later. Let's look at the first one. So the label space relationship means that how do you assume the availability of labels in the source and target domain? As you know, in the visual domain adaptation, we have both source and target domain in training, that in most settings. Then the labels might be available, might not be available. Then how to consider that? Here we list in total 6 different settings by considering different types of label space relationship. The first one is the most traditional one. In UDA, the very simple setting. So here I want to introduce this kind of notations first. So we use the solid circle to represent the source domain and the dashed circle to represent the target domain. And we use the solid symbols to represent label data and these empty ones to label unlabeled data. So we will use this kind of notations across this tutorial. Okay, for any model training, let's consider 2 different phases. The first one is training phase and second one is testing phase. During training phase, we have source domain and which are fully labeled. In most scenarios, we assume we have abundant images with labels for everyone. Here, for simplicity, we only show two classes. One is cross, the other one is circle, and they all have labels. And for the target domain, we also have a number of samples, but we don't have any labels. Then we will train the model based on the labeled source domain and unlabeled target domain. So the unsupervised domainization, this term unsupervised mainly refers to the absence of labels in the target domain. But for the source domain, we still have labels. That might be a confusing part, but I want to clarify that. During the testing phase, we only focus on the target domain, and of course, we don't have labels.
Many machine learning models assume that training and test data come from the same distribution. However, in real-world applications, this assumption often does not hold. So what causes domain shift? Let's look at some common sources of domain gaps. Given these challenges, the goal of domain adaptation DA is to reduce the domain shift so that models can generalize better across different datasets. There are several common types of domain adaptation, as shown in this slide. In this presentation, we focus on unsupervised domain adaptation (UDA), where we only have labeled data in the source domain and unlabeled data in the target domain. Now, let's move on to the core of this presentation: how ADDA leverages adversarial learning to solve the UDA problem. Now that we understand the challenge of domain shift and different settings of domain adaptation, let's introduce the key method of this paper: Adversarial Discriminative Domain Adaptation (ADDA). The core idea of ADDA is to learn a mapping that transforms target domain images into a feature space that matches the source domain. This is achieved through adversarial training, where a domain discriminator tries to distinguish target features from source features, while the target encoder tries to fool the discriminator. Now that we understand the key idea behind ADDA, let's break it down into its three main steps. In the first step, we train a CNN encoder using labeled source domain images. The encoder extracts features from source images, and a classifier is trained on top of these features. This is a standard supervised learning process where the model minimizes the classification loss on the source domain. In the next step, adversarial adaptation, we introduce a separate target encoder, which learns to map target images into the same feature space as the source domain. However, since the target domain is unlabeled, we use an adversarial training approach. How does adversarial training work? We introduce a domain discriminator, which is trained to differentiate between source and target features. The target encoder is trained to fool the discriminator, so that target domain features become indistinguishable from source features. This is similar to GAN training, where the encoder plays the role of a generator, and the discriminator acts as the adversary. Finally, once the target encoder has been trained, we can apply the model to unseen target images. During inference, target images are passed through the target encoder, which maps them to the shared feature space. The same source classifier trained in Step 1 is then used to classify the target samples. Since the target encoder has been adapted, it ensures that target features align with source features, allowing for improved classification accuracy. The figure below illustrates 3 steps in the ADDA method. Dashed lines indicate fixed network parameters. Before we compare ADDA with GAN, let's briefly review how a generative adversarial network works. A GAN consists of 2 networks, a generator G and a discriminator D, which compete in an adversarial game. Input: latent vector Z. Output: fake image generated by G. Generator G deconvolutional layers maps 1D latent vector Z into fake image that confuses discriminator D. Discriminator D convolutional layers plus fully connected layers distinguishes image into real or fake binary label, i.e. 0 for fake, 1 for real. Over time, G improves until it can generate highly realistic images. Let's look at the core similarities between ADDA and GAN. First, adversarial training. Both ADDA and GANs rely on a discriminator to distinguish between 2 distributions. In ADDA, the discriminator classifies source versus target domain features. In GAN, the discriminator classifies real versus fake images. Second, ADDA optimizes the target feature extractor to fool the discriminator, just like the GAN generator fools the discriminator. Both methods involve adversarial loss to push one network to improve. Finally, feature distribution matching. In GAN, the generator aligns fake image distribution with real images. In ADDA, the target encoder aligns target feature distribution with the source features. Now that we've discussed the ADDA method, let's take a look at how the authors evaluated its performance in different domain adaptation scenarios. The paper evaluates ADDA for unsupervised classification adaptation across 3 different settings, covering both digit classification and real-world domain shifts. The first experiment focuses on adapting between popular digit datasets, MNIST, USPS, and SVHN as shown in the left side of the figure below. The second experiment is a more challenging cross-modality adaptation task, using the NYU depth dataset. The goal is to adapt models trained on RGB images to work on depth images without labeled depth data. The third experiment evaluates adaptation across different domains in the Office dataset. The first table shows experimental results on unsupervised adaptation among MNIST, USPS, and SVHN. On the easier MNIST and USPS shifts, ADDA achieves comparable performance to the current state-of-the-art. ADDA achieves convincing results on the challenging SVHN and MNIST task in comparison to other methods. In contrast, Kogan are not able to converge on SVHN and MNIST because the domains are so disparate. In the second table, we can see the adaptation results on the NYUD dataset. ADDA greatly improves classification accuracy for this task. For certain classes, i.e. counter classification accuracy goes from 2.9% under the source-only baseline up to 44.7% after adaptation. In general, average accuracy across all classes improves significantly from 13.9% to 21.1%. Finally, in the Office dataset, ADDA achieves strong results on all 3 evaluated domain shifts. and demonstrates the largest improvement on the hardest shift, a Amazon right-pointing arrow W webcam. In conclusion, ADA is an effective approach for unsupervised domain adaptation (UDA) using adversarial learning. By aligning feature distributions between the source and target domains, ADDA allows models to generalize better across domain shifts. Achieves state-of-the-art results on multiple domain adaptation tasks. Works well in unsupervised settings, where labeled target data is unavailable. Adapts effectively across digit datasets, cross-modality tasks, and real-world Office dataset shifts. Despite its effectiveness, ADDA has some limitations that future work could address. Since ADDA relies on adversarial learning, it inherits common GAN problems. Mode collapse. The target encoder might fail to generalize well. Convergence issues. Training stability depends on careful tuning of the discriminator and encoder. ADDA focuses purely on aligning feature distributions, which works well for classification tasks. However, it may not be optimal for structured tasks like semantic segmentation, where spatial relationships are important. Before diving into training, let's briefly introduce the CNN architecture used in ADDA, LeNet. LeNet was proposed by Yann LeCun et al. In 1998, originally designed for handwritten digit recognition. It consists of two convolutional layers, each followed by a max pooling layer, and is a foundational architecture in deep learning. This is the code to train the source CNN in the first phase. In the second phase, this is the architecture of the discriminator. The target and source CNN models share the same architecture. Now that we've trained the source CNN, let's move on to the adversarial training phase, where we optimize the discriminator and target encoder in alternating steps. The key idea is that we train the discriminator and the target CNN in separate steps, ensuring that only one of them is updated at a time. We do this by setting their requires_grad properties accordingly. In particular, we first train the discriminator by setting its requires_grad variable to true and that variable of target CNN to false. When training the target CNN, we switch the values of these variables. Now, let's look at the final results after training ADDA and compare its performance on the target domain before and after adaptation. High accuracy on the source domain 98.75% shows that the model is well trained on the labeled source dataset. Poor performance on the target domain 43.36% without adaptation confirms that domain shift negatively impacts model generalization. After applying ADDA, the accuracy improves to 67.93%. Proving that adversarial learning successfully reduces the domain gap. Here are some references that. Thank you for your attention.